Welcome to our exciting journey into the mysterious world of irrational numbers. Around 400 BC, a group of ancient Greek mathematicians known as the Pythagoreans discovered that not all numbers could be written as simple fractions, those of the form p over q, where both p and q are integers and q isn't zero. These special numbers that defy this fractional representation are called irrational numbers. Imagine discovering a new type of number. It was a mathematical breakthrough. Examples include the square root of 2, square root of 3, and the famous constant pi. All fascinating because they cannot be expressed as exact ratios. Before we dive deeper, remember when we use the square root symbol, especially in this lecture. It refers to the positive square root. For example, the square root of 4 is 2, although negative 2 squared is also 4. Let's think about why irrational numbers matter. They show us that the number system is much richer than just fractions and whole numbers, opening doors to advanced geometry and calculus. As we proceed, we'll explore how these numbers connect to the number line and how you can visualize them. Let's get formal now. A number as is called irrational if there is no way to write it as a fraction p over q, where both p and q are integers and q is not zero. In other words, these numbers cannot be pinned down to a bouncing fraction. Just like there are infinitely many rational numbers between any two numbers you can think of, there are infinitely many irrational numbers too. Some famous examples you probably know are the square root of 2, the square root of 3, and even pi. Also, consider a number like 0.101010111101110, which goes on without repeating. That is an irrational decimal. It's very important to understand that every irrational number corresponds exactly to a unique point on the number line. So these numbers are very real and very visual, even if they cannot be written neatly as fractions. Mathematicians have shown this wonderful one-to-one correspondence between real numbers, which include both rationals and irrationals, and points on the number line. This means the number line truly visualizes all real numbers. Let's take a moment to appreciate a beautiful discovery from the 19th century by two brilliant German mathematicians, Richard Dedekind and Georg Cantor. They showed that the entire collection of real numbers, which includes every rational and every irrational number, can be perfectly represented on the number line. This means that for every real number you can imagine, there is exactly one unique point on the number line that matches it, and vice versa. Every point on this continuous line belongs to exactly one real number. This one-to-one matching, or as mathematicians call it, a bijection, guarantees that the number line is not just a line with some dots, but a complete continuum holding infinitely many numbers, including all those tricky, irrational ones. Because of this incredible relationship, the number line earns the name real number line. It's foundational to many fields of mathematics, including geometry, calculus, and beyond. Imagine the richness of this number line, smoothly stretching from negative infinity to positive infinity, neatly containing every rational and irrational number within. Let's now learn how to locate an irrational number, the square root of 2, on the number line using a classic Greek geometric method. Start with a square named OABC, where each side is exactly 1 unit long. This means OA measures 1, and AB also measures 1. According to the Pythagorean theorem, the length of the diagonal OB of this square is given by the square root of the sum of the squares of the two sides, OA and AB. So OB equals the square root of 1 squared plus 1 squared, which is the square root of 2. Next, we use a compass centered at point O and set its radius to OB, which we found is square root of 2. When you swing the compass, the arc it creates will intersect the number line at a point we call P. This point P beautifully represents square root of 2 on the number line. It's not just a number in theory, but a tangible point you can locate geometrically. Isn't it fascinating how geometry helps us visualize such tricky numbers? Try picturing this. The diagonal stretches further than 1 unit but less than 2 units, giving us a precise spot for the square root of 2. Here is a practical example to strengthen your understanding. We want to locate the irrational number square root of 2 on a number line. Given a square OABC where each side measures exactly 1 unit, our first step is to construct this square accurately. Next, applying the Pythagorean theorem. The diagonal OB equals the square root of OA squared plus AB squared, which is the square root of 2. With a compass, place the pivot at point O and open it to the length OB. This is our radius. Now, swing the compass to create an arc intersecting the number line. Where the arc meets the number line is point P. This point uniquely marks the position of the square root of 2. This simple, stepwise geometric method allows us to visualize and precisely locate irrational numbers, giving them a tangible place on the infinite number line. Does anyone want to try constructing this at home? It's a wonderful way to experience how numbers and geometry physically connect. Building on the method for square root of 2, let's see how we can locate square root of 3 on the number line using a clever geometric construction. Recall we had the point B representing the square root of 2 on the line we obtained earlier. Now draw a line BD perpendicular to OB with length 1 unit. Here comes the magic. Using the Pythagorean theorem, the length from O to D, denoted OD, is the square root of OB squared plus BD squared. Since OB is the square root of 2 and BD is 1, this becomes the square root of the quantity open parenthesis. The square root of 2 squared plus 1 squared, close parenthesis, equals the square root of 2 plus 1 equals square root of 3. Now, setting the compass at O with radius OD, swing an arc to intersect the number line at point Q. This point Q uniquely indicates the position of square root 3 on the number line. This shows how using simple perpendicular lines and Pythagoras' theorem, we can graphically represent more complicated irrational numbers, making the abstract more visual and understandable. Visualize how the number line, the compass, and the right triangle work all together to locate this beautiful irrational number precisely. Let's practice locating the square root of 3 by following this example step by step. Starting with the point B that represents the square root of 2, we construct a line segment BD perpendicular to OB, measuring exactly 1 unit. Applying the Pythagorean theorem, the length OD is the square root of OB squared plus BD squared. Since OB is the square root of 2 and BD is 1, this simplifies to the square root of 3. We then place our compass needle at point O and set the radius as OD. Swinging the compass, the arc intersects the number line at point Q. This point Q marks the location of the square root of 3 on the number line. This clever use of perpendicular lines and distance measuring lets us precisely pin down square roots of integers that are irrational. Try to picture how these geometric steps connect neatly with algebraic reasoning, deepening your understanding of irrational numbers and their representation. With the techniques we've learned for square root of 2 and square root of 3, a powerful general method emerges to locate square root of n for any positive integer n. Once you have found the point on the number line that corresponds to the square root of n-1, you draw a line perpendicular to the number line at this point with length 1 unit. By applying the Pythagorean theorem again, you find the distance from the origin to the endpoint of this perpendicular segment. This distance equals the square root of n. Using a compass with the origin as the center and radius set to this length, you draw an arc to intersect the number line. The intersection point represents the square root of n. This step-by-step geometric technique allows you to visualize irrational square roots methodically and accurately. Try to picture this as a staircase climbing higher with each step representing the next square root, each one constructed from the previous, linking geometry and algebra beautifully. Let's put our general method to the test and locate the square root of 5 on the number line. We know that the square root of 4 equals 2, which is easy to locate. Starting at point 2 on the number line, our first task is to construct a perpendicular segment that measures exactly 1 unit. This perpendicular segment will be our key to finding the square root of 5 geometrically. Label the endpoint of this perpendicular BD as point D. This sets up a right triangle, OBD, whose sides we will use in the next step. Stay tuned for part 2, where we calculate the length OD to find the square root of 5 and pinpoint it on the number line. Continuing from our previous step, we now have a right triangle with sides OB equals 2 and BD equals 1. Using the Pythagorean theorem, the length OD is the square root of OB squared plus BD squared, which calculates as square root of 2 squared plus 1 squared equals square root of 5. Next, we place the compass pivot at the origin O and open it to the length OD. Swinging the compass, draw an arc that intersects the number line at point Q. Point Q marks the location of the square root of 5 on the number line. Through this geometric approach, we are able to neatly construct and visualize irrational numbers beyond simple squares. Try to imagine how this process can continue infinitely for all positive integers, unfolding the number line's rich structure. Now it's your turn to practice. Try locating the square root of 6 on the number line using the methods we've explored. Start from the square root of 5 if you like, and construct a perpendicular of length 1 unit. Next, see if you can build on that to mark the square root of 7, and then estimate the square root of 10 as well. Remember, each time you utilize the perpendicular segment and the Pythagorean theorem to calculate the new length. Drawing precise diagrams helps enormously. Use your compass to swing arcs, intersecting the number line at new points. Don't worry if it seems tricky at first. These constructions beautifully connect algebra with geometry, and with practice, they become intuitive. If you get stuck, think back to the steps we took for the square root of 2 and the square root of 3. Enjoy exploring these fascinating numbers on the number line. Let's wrap up our lesson by summarizing the key ideas. Irrational numbers, unlike rational numbers, cannot be represented as fractions. Their discovery by the Pythagoreans marked a turning point in mathematics, revealing the richness of numbers beyond rationals. The set of real numbers unites these two worlds, rationals and irrationals, into a continuum represented perfectly on the real number line. This number line lets us visualize each real number as a unique point, making the abstract real and accessible. Using geometric tools and the Pythagorean theorem, we can locate irrational numbers such as square root of 2, square root of 3, and others on this line. This connection between geometry and algebra illuminates how mathematics is a tapestry woven from multiple beautiful threads. As you continue your mathematical journey, remember how these foundational ideas will underpin your understanding of geometry, algebra, and calculus. Keep exploring and stay curious about the numbers that build our mathematical universe.